Okay, so it's a great pleasure for me to introduce Guy Casale from Université de Rennes, and he'll speak about algebraic solutions of Kummer equations.
Thank you, Ronnie. So I thank the organizer to give me the opportunity to talk about this very particular differential equation I have met something like 20 years ago and I'm working with since. So I decided to call it Kummer equation, but because the first instance of this equation appear in Kummer paper, Kummer work on hypergeometric function and hypergeometric equation. But this week, some colleagues just told me that it was not a good idea. There are other things called Kummer equation. So I hope you are not waiting for the other things. And Kummer equation is this red equation that you can see here. So there are two ingredients in this equation. There is a rational function that I call R that sometimes will be an algebraic function. And you have this Schwarzian derivatives, yes, right here, classical Schwarzian derivative. And then what I will call for this talk Kummer equation is this equation here, the red one, relating the Schwarzian of the unknown to this strange expression just here. So when I will take R to be an algebraic function, this means that I will work on an algebraic curve, which is a ramified covering of the projective line, and I will see everything on this algebraic curve, and the derivation with respect to y also. So I will lift everything above.
So now the derivation is with respect to x, right?
Respect to x, yeah. Maybe I can add here. Prime is a derivation with respect to x. Okay, and so I made this equation because of this very nice property that you get here, that this equation in this particular form is compatible with a composition of functions. So if you evaluate this operator PR onto a composition of two functions, you get such equality that is in some sense generalizing the same equality for the Schwarzian equation. So maybe you know that you put R equal to 0 and you have just PR is a Schwarzian derivative. And you may remember that this Schwarzian derivative satisfies something like that. So because of this compatibility with the composition, okay, this equation say that if PR of F is 0 and PR of G is 0, then the composition is a new solution of your equation. Because of this compatibility, this equation appear in the work of some mathematician on Lie pseudogroups here. Yeah, so I just gave three names, mainly the principal names about people working on Lie pseudogroup that are Lie, Cartan, and Vessio. And so in some place in their work, you will appear this equation here, the red equation that is here. And so what is the Lie pseudogroup? Roughly speaking, it is a set of holomorphic solution of partial differential equation that are stable by composition when you can do a composition. Usually, if you have solution of partial differential equation, it is not always true that the range of one of the solution will be the domain of another one. So you may think of this also, but I have no big reference for that, as a Ritz differential groups. As you know, Ritz has his own definition of what is a differential group, which is a kind of formal group defined by differential equation. And this Kummer equation will give you instance of Ritz differential group which is different from Colchin differential group. And this is not Colchin differential group. Okay, so this is a point of view we will use on this differential equation. But this equation appears in other part of mathematics. For instance, you have another place where it appears. It's a Retyper theorem about permutable function. Permutable function. Yeah, so you take two rational functions that commute. You want a list of this couple of functions that commute, and then you have just to look at Retyper, and it will give you all the rational function in one variable satisfying that. And in this in this paper, again, this equation, okay, not directly, but at some point, this equation appears also. Okay, I don't understand this paper, so I cannot say more about that, but there is a third work of Reed where this equation appears. So it is known as a Retyper Transcendency Theorem. So it's about a solution of a Q difference equation, the red equation here. And the fact that solution of this equation usually do not satisfy any differential algebraic equation. But there are some counterexamples. So you take f, a rational function. The degree of f is bigger than 1. You can assume 0 is a fixed point with a multiplier which is bigger than 1. And then you look at a solution of this difference equation, which is a nonlinear first order and autonomous Q difference equation. And you look at the solution that is, there is one solution that can be written as a convergent power series and starting with a z plus higher order term. So the existence of such a solution is a theorem from, I think, Koenig's, maybe Koenig's Poincaré. And then you had this condition that f is differentially algebraic. Then if you had that, you will have very few possibility for your f here. Yeah. F as a rational function is conjugated to a monomial, a Chebyshev polynomial, or lattice rational map. Here, by conjugated, I mean that if you replace f by f with h minus 1, with h, which is a fractional linear map, so something in PSL2 of C, and up to this transformation, you will have one of these, something in one of the three families. Yeah, so basically, monomial are related to the exponential. Chebyshev, I don't know how to write Chebyshev, so maybe, okay, I write like I can read. So Chebyshev is related to the cosine function, and the lattice, in the same way, the monomial and Chebyshev are related to their function. Lattice is related to Weierstrass P function. And so again, if you read the proof of Reed, he did some kind of elimination theory. So he starts with a differential equation, let this Q difference equation act on the differential equation, and then he did elimination. And at the end, he ended up with Kummer equation. So he had Kummer equation, and then he did more work on Kummer equation that here. Okay, so, but this proof is quite, okay, it is not so easy to follow. So a part of this talk is to show you that using idea from pseudo-group theory, you can reorganize the proof of Reed basically in two steps. So I don't know why I wrote lemma here. There are like steps of the proof. Yeah, so the first step is find a rational function R, or prove that there exists a rational function R, such that your f that appear here, that is your equation, satisfy a Kummer equation. And then you just look at all the, then you study directly this problem, and you can find all the rational solution of Kummer equation. So rational solution of Kummer equation are given by the list of root. There are no more. So I will try to extend this theorem now, replacing this f by algebraic function and not rational function. And then the first step is the same, but the second step is to understand all the algebraic solution of Kummer equation. That's the reason of the title here. So let me just say something about other work where this Kummer equation appear, in case someone understand, you can explain me. So there is this theorem by Jean et Al, saying something about, so not rational, but holomorphic maps. Like, okay, maybe. I have now the chat somewhere. And I go back here. So if you look now at germs of holomorphic function having this shape, so the dot are for higher order terms, then Jean et al. Associate to this f some invariant that are some numbers ai for I in Z that characterize its conjugacy class. So now conjugacy means f phi minus 1 with phi, it's something in Z, C of Z. Yeah, so it's a convergent power series without constant term. And so all the conjugacy class of such a map is completely described by a set of invariant, and binary mean only there exists a P such that only AP and A minus P are different from 0, and all the others are equal to 0. Okay, and he proved that binary diffeomorphism is binary if and only if it is conjugated to a solution of a Kummer equation. Yeah, and Kummer equation means with a rational R, not holomorphic version of this equation. So it is done in Ekal resurgent function books. I don't know if some of you have read this book, but they are not so easy. And it is in the second volume. You can find elements that show you this theorem, but I will be very happy to meet someone that understands this part of Ekal work and that can be show me how to prove that, because these Kummer equations that appear are very, very special. So if you believe in this theorem of Ekal, it will imply that this binary map that appear here are never rational. So they are never rational function, because you know the rational solution of Kummer equation, they are in read list, and there are no element in read list with a so-called fixed point, a parabolic fixed point, meaning that can be written f of z equal z plus higher order term. There is no in read list. So this kind of map are, so it's a kind of irrationality result. Okay, so what I want to look at is how to use the algebraic pseudogroup structure to organize root proof and generalize some of this. So I will say something about the algebraic pseudogroup and that appear in this context. So this is a rough definition. So an algebraic pseudogroup is a set of holomorphic transformation that is stable by composition and by inversion when they exist. And this set must be defined by algebraic differential equation. So it is algebraic differential equation, but you are not looking at solution in some abstract differential field, but in the sheaf of holomorphic functions. And so here are some basic facts about that. The first one, which come back to Lee, I think, is that any algebraic pseudogroup is in fact included in the solution set of a Kummer equation. So Kummer equation have this property to define algebraic pseudogroup, and they are maximal. So maybe I should say any proper, as you can always take 0 as your differential equation and you get everything. So any proper algebraic pseudogroup is included in the 0 set of Kummer equation. And then you can look at the possibility for smaller algebraic pseudogroup. And here are 2 examples. So the first one that I called A, it's defined by this equation here. Yeah, so A is the operator, and you take the 0 set of these things. You can verify that this is stable by composition when composition is well defined, and that it is a sub pseudogroup of the one defined by Kummer. Okay, it is due to this big equality here, saying that if you are a solution of A, then you are a solution of P, and the relation of the small r and the big R is given by this Riccati equation. I don't know how to write Riccati neither, so. And you can do the same for first order. You have first order example, which are this shape here. And also this first order equation define a subset of this A equation if you have such a relation between M and R. So we have here example, but what we want is to find all the pseudo group and all the sub pseudo group in order to have a clear picture of what is going on. And here there are just examples. So I don't know if it is possible to prove directly that these are the only example, but a nice way to do that, and I will use it to introduce some object I will use, is to look at its Lie algebra. So as it is something looking like a group, it has something looking like a Lie algebra. And it is in fact a sheaf of Lie algebras of vector fields on the line, defined by differential equation. So here is again a rough definition. So what is this object that I will just call Lie algebra in the talk? There are solution set of linear differential equation over your ground field, such that if you take 2 solutions, when I say solution, it means solution holomorphic somewhere, and that are holomorphic on the same domain, then this new function here is a new solution. So where does it come from? It's just that you have to interpret this as the coefficient of vector fields on the line. And when you do the Lie bracket of 2 vector fields, you obtain a 3rd vector field this way. And so this solution, this equation here, just means that if you interpret solution as vector field that are solution, then the solution are stable by the Lie bracket. So it defines a sheaf of Lie algebra of vector fields. And if you start, and so this is a general definition, but now you can go from a group or pseudo group to Lie algebra or sheaf of Lie algebra. by the usual technique, taking the linearization along the identity, like for the group. And here it can be written like this. You take an holomorphic vector field, you compute its flow, so its flow given by a Cauchy theorem. And then you ask for condition on A such that this flow is, for any value of t, is always a solution of this Kummer equation. And then you obtain the linearized equation, which is here, that I call the Lie of PR. Okay. And this is this third order equation here. It is a third order equation that maybe some of you recognize this equation. It's already appear when you want to study second order differential equation. If you're looking at this equation, maybe I will do some mistake, maybe it's plus r of x u equal to 0. Then you go from this second order equation to this third order equation by looking at a equal u square. So it is called a second symmetric power of this equation. So in fact, it's a third order equation, but it looks like a second order. Now, if you translate everything on the Lie algebras, things are much easier now, because you have just to look at linear equation and you want to understand if there are vector subspace of solution, strictly vector subspace of solution that are stable by these things here. So you can do it properly, looking at a second order equation that defines subspace of solution stable by this operation, order 1, etc. And then in each case, you will just find the Lie algebra of the, I will go back, of one of these pseudo group here. So here is in fact the list of all the pseudo group included in Kummer equation. And you see that it is not clear that Kummer equation has sub-pseudo group, because you need to solve a Riccati equation here, to be able to find an equation like this whose solutions are included in solution of P. Okay, so this is this theorem that is written here. So remember that the equation we are looking at is this one that I call PR. And the Lie of PR is a third order equation, which is a symmetric power of a second order equation. This means that its Galois group is always included in PSL2, seen as a subgroup of GL3 by the action of the quadratic form, or by the adjoint action, the same. So if you assume you have equality, so I will erase that. You assume you have equality here. Then there are no sub-pseudo group of your Kummer equation defined over this field, okay, except order 0. And in fact, it is an equivalence between the two. It is equivalent because both are equivalent to the condition that this equation, as a Riccati equation in small r, has an algebraic solution. So this tastes like other kind of theorem we know about, solutions that have such that equations such that the solution do not satisfy any differential equation unless they are algebraic. But it is much easier to prove because we have all this Lie algebra business that can be used to simplify all the proof. Okay, and as I said, I'm interested in algebraic solution of this.
So we have a question in the chat asking what Galois, the Galois here.
Yeah, it's Galois group of the, yeah.
It's a Galois group, yeah.
Galois, I mean the Galois group of the linear equation. And this is funny, funny, I don't know if it is funny, but you see the Galois group is itself an algebraic group, so it has a Lie algebra. But here we are looking not at the Lie algebra of the Galois group, but the Galois group of the Lie algebra. Yeah, and in fact, you can present this PR as a Galois group of something else. So you can look at the Lie algebra of the Galois group of the Lie algebra of the Galois group, and maybe you have to stop somewhere. So, but here is okay, the Galois group of the linear equation, this one here, which is the projectivization of the Galois group of this equation here. Okay. And so now among all algebraic solution, you have two types of algebraic solution. You have the one that are in an order 0 subgroup, pseudo group, and you have the others. And this one, they are quite easy to understand. There are not a lot. You cannot have infinitely many of them, but this one are quite challenging to understand. And for instance, because of this one, you can have example of Kummer equation whose set of algebraic solution is Colchin dense. So the set of algebraic solution, all the algebraic solution, they do not satisfy a simpler equation than just your order 3 differential equation. But there are transcendental solution, no? Because the Galois group is PSL2. Okay, let's go to our result about the extension of Retyper theorem. So now we are looking at this Q difference equation, which is algebraic, autonomous, order 1, that you can write, if you prefer using an algebraic function, you can write f of qz equal the same as in the Retyper theorem, but now f is algebraic, not rational. Q is always a big enough complex number, and f is a solution of this one. Now there are few theorems that ensure that you have a solution, but you may assume you have one. And then if f is differentially algebraic, then the first step of our proof, remember there was 2 steps. First, prove that if f is differentially algebraic, then the equation, so this f here, is a solution, or maybe this f is a solution of this, an algebraic solution of this differential equation. And then the second step is to study the algebraic solution of this one. So this is okay, this is true. And then you can look at the solution. So I think 3 or 4 weeks ago, Lucia Divisio and Gladys Fernandez put on archive an article where they have a more precise, much more precise result, assuming that your solution is a convergent power series, your solution f. Then they can prove that, in fact, this f, which is here, is in an order 1 sub-pseudo group, as it is for Retyper list. And so I'm pretty confident that they will show that, in fact, if you assume f is a convergent power series, then you will have only the case that already appear in Retyper list. There are no other case where such a function can be a differential algebraic. But there are other examples not satisfying this hypothesis. And I will end with this example. The example is coming from the J function, the classical J invariant, which is which realize a quotient of the upper half plane by this the modular group PSL2 of Z. And then there are many, many things that we know about this J function. And if you look carefully, you will see that there exists a rational function here such that this equation is satisfied, meaning that J is differential algebraic. Okay, so it is one of the things we want to see. And then if you take any 2x2 matrix, invertible, rational coefficient, positive determinant, then you will find a polynomial in 2 variables, such that G of evaluated in J of Z here is for the homography, the fractional linear map associated to this matrix. They are related by some polynomial relation. And for instance, if you take G, which is just a 2, 0, 0, 1, then you will take some polynomial P2, such that P2 of 2Z, G of Z equals 0. And so this is, J is a solution of some Q difference equation, the kind of Q difference equation we want to look at. So it is an example, but it is not an example that is in Lucia and Gladys' work, because 0 is not there. Yeah, so J cannot be expanded as a power series around 0. And many very nice property, or very bad, I don't know, property about this J function that so you may verify by direct computation that all the algebraic functions that are defined by this special polynomial there are algebraic solution of your original Kummer order 3 equation. But you can also prove the other. So all algebraic are, and all algebraic solutions have this shape here. So this sense from the left to the right, it's easy computation, and the other, it is not. So the only way I know is to use Jonathan Pilar result about J function characterizing this kind of things. So so it is not easy. Okay. And and remember that this is this equation there. It looks very much like the equation of the J function, but there is something instead of 0 here. So the other nice property is that you have equality here, which is quite direct to prove. And then what you can also prove is that if you look at the set of algebraic solution of this one, this is an instance of order 3 differential equation with set of algebraic solution, which is Zariski dense. And that does not admit any second order. Okay, we cannot prove this way, but you can add also that there, because of this condition, there is no order 1 or 2 pseudogroup, algebraic pseudogroups. Okay, there exists even stronger result, but this one is very elementary to prove. There is a stronger result that, in fact, there are no order 1 or 2 differential equation satisfied by solution of this type, unless they are algebraic. But it's much more difficult to prove this more general statement. So I propose to stop here on this example.
All right, perfect.
And then I have other things for later.
All right, perfect. So let us thank Guy for the first part of his talk. All right, so let's restart. So let me just say before Guy goes on, do we have any question that we might ask him about the first part of his talk at this moment?
Well, I may have a question. So in the cases that you have considered, the Galois group of the Lie algebra is the whole PSL2.
Yeah.
Is there any other situation where it is not the whole PSL2?
Yeah. In fact, so the Lie algebra is always given by a third order differential equation like this one.
Yeah.
So the Galois group of this one is the same as the Galois group of this second order equation. So each time you have a smaller Galois group here, you will have another one. And an example is if you have an algebraic solution, small r, of this Riccati equation, then the Galois group is strictly smaller. So you can build R in the opposite way. Right. You start with a small R, put it in, you get a big R, and this will not satisfy this equality here.
Oh, okay. So have they been? Is that, so that's the only way you're saying then?
The only way, yeah.
The way, okay.
All right, any other question at this point?
Well, I have a question, but it's the same question that you had because we were in the same breakout room. But I'll ask it because you're the organizer, so I should. Okay, so yeah, I have a question about this comment you made. There was a theorem which was an if and only if result, and you mentioned that one direction was harder. And the only way to do it was to use some result of Jonathan Pila.
Yeah, this.
Yeah,
okay. I didn't say the only way. The way I know.
No. I mean somehow. Yeah. Sorry. Can you just explain this result again? I think I missed something about it.
So you have this. I will clean everything here. Yes. This is. Okay, I'm cleaning everything up. And then you have this differential equation here. Yeah? And you want to understand the algebraic solution. And what I'm saying is that if you build this polynomial here from a G in this group, that I don't know how to compute this polynomial, but there exists. And then you take the algebraic function defined by this polynomial, then there are algebraic solutions of this equation. So this is an easy way. You just take the derivatives and everything. So you write, in fact, something like J of G of Z is equal to F of G of Z, and then you compute Schwarzian derivative in both sides. So you apply PR, PR, both sides, and you will get that your F here satisfies this equation. But now, if you want to go the other side, you start with an algebraic solution. So you have something that satisfies this equation. You're not sure you will get such a G here. Yeah, so you have to work on that. And so I said Pila, but in fact, this is something we did also, some way to build this G from this F here. So maybe.
Yeah, but I have some question. Maybe I don't understand. Maybe I missed some of the notation a little or something. But
yeah.
So where are these solutions? These are algebraic over J of Z, or
no. These F are just algebraic function over Q.
Yeah.
They are in polynomial of this. Then you evaluate them in J. The J is really the holomorphic function, not living in somewhere. It's just really holomorphic. So this is an algebraic function. The composition is algebraic over J, but it's just an algebraic function composed with this one.
Yeah. Okay. I understand now. Yeah.
All right. So if we don't have any more questions, and thanks, James, for asking the question, you can continue, Guy.
Okay. So there are two slides for what followed. The first one is about some conjecture, that something that I would like to, maybe it's optimistic, but something I would like to prove in order to finish this proof of the extended Rit theorem that is not finished. We do not have a list. So, and then some example where the conjecture can be proved. So the conjecture is here. So you start with an algebraic function and an algebraic solution of this big differential equation I just talked about. And you assume the Galois of the Lie group of the Galois group of the Lie algebra. So remember that this means A third plus 2R A prime plus R prime A equals 0. This is our differential equation. is the maximal group it can be. And assume that F is not a solution of an order 0 subgroup. As I said, these solutions are well known. I will explain then how they fit in this context. Then I want to prove that there exists a function group into PSL2C. In fact, it is function, so it is in PSL2R. With pi, the quotient map, and the quotient will be a Zariski open subset of some curve. This is an algebraic curve that you can think it a projective algebraic curve, compact algebraic curve over C. So I want to prove to find such a group, and a map from a curve Y to another curve. They are both curves, complex curves, Y and H, such that, so first, the R you're starting with is a rational function on Y. So you control the place where the ramification and all this. And second, there exists a G in so-called the commensurator of this group here, which in the case gamma is equal to PSL2 of Z. This will be equal to PGL2 of Q with a plus here. There exists some G here, and with an associate polynomial. So the associate polynomial is this one. You take pi, the projection, like pi is what we called before J. Yeah, it is a quotient. So this is for exactly the same reason as for J. There exists a polynomial here in two variables satisfying this. And then your F here, the F you start with, which is an algebraic solution of your Kummer equation, which is not in an order 0 subgroup, then it satisfies this equation that is here. Yeah. So it gives you the list of the solutions that are differential algebraic if you impose this condition here. So it will, okay, because then your solutions are just, let me write this, X, Y. Your solution will be something like H, yeah, your solution F of your equation QZ equal to F of small f of Z. F will be something like pi composed with the inverse of H. So this is a rational map, okay, algebraic, between two algebraic curves. And so F will be something that you can write this way. And pi from H to this will satisfy an algebraic differential equation as the J function did. And composed with this H, it will satisfy another differential equation also. So this is differential algebraic, and this is solution of this equation for the F coming from this particular polynomial relation here. Yes, as H is just kind of polynomial, and big P is also one. So what happens if, for instance, F is solution of an order 0, then you can erase the P. So I will write it in blue. So without condition on the Galois group, if F is solution of an order 0 pseudogroup, sub-pseudogroup, then you will have that H, that F satisfies something like this. You have a big function H, and your F is algebraic, but defined by an equation like this with H rational. So it is a very, very special kind of polynomial P, and then you do the same job, but now you do not need that. So it's very special F. Special F. And this will imply that the solution of your differential, so you write this F, roughly F is H minus 1 H of X, but now you cannot cancel these two because this is not uniform. And then you solve your linear equation that I wrote, your Q difference equation that is here. And then the F you get here is in fact, I would say periodic. Yeah, so if you compose F many times itself, you will get the identity. Now, if you look at the condition on Q, that is bigger than 1, it will give you a contradiction. So this is not a solution of order 0. It may be tackled by this condition here. So you can probably erase that, okay? But this, what I just told you here, there are some lacks somewhere, okay? I'm hiding them, but there are some gaps. And so this is a conjecture here that we want to be able to build this group, to find all this, and to build our polynomial and find our special, very special F here, defined by very special polynomial. So there are some particular case, and so to understand this particular case, you have to write this Kummer equation in a different form. So you have to use a Schwarzian primitive equation. So you look at function IH, whose Schwarzian derivative is this R that is here. Okay. Then you can rewrite Kummer equation in this way. Yeah. So the solution are the function here, Y, such that H composed with this function has the same Schwarzian derivative than the original H. So this is, again, it's just computation to see that this will imply Schwarzian of Y plus R of Y prime square equal to R of X. So it is equivalent. But you are using this, this is no more algebraic. This is, okay, solution of an equation. It is transcendental function. It is differential algebraic, but transcendental. So now there are some points where you can build this group gamma and all these things. So it is the case, for instance, where R, okay, so if R has pole of order bigger than 2, yeah, it's a rational function. If there are big enough poles, then F must be a solution of an order 0 subgroup. So to see that, you just have to look at this equation. And this equation is, again, basically the equation I wrote before. Maybe there is a minus if I put this way. So this is R. This is this second order linear equation. And you know many things about that, especially the poles that have order bigger than 2. There are irregular singularities. So a solution defined in a sector that end at this point, they must have exponential growth or exponential decay because the point is irregular. And when you compose, yeah, with an algebraic, now remember that you want to study algebraic business. So F is algebraic and it's an algebraic solution of this one. So if you compose H with an algebraic function, you will not change this exponential growth or exponential decay. So the set of pole of order more than 2, they are stable by F. You cannot move in another place. And if you look carefully at the normal form of solution of this near an irregular singularity, yeah, you will see that when you compose this a certain number of times, you will get the identity. And this will give you the order 0 subgroup that contain F. So if you assume F is not solution of an order 0 subgroup, then the only poles have order less than or equal to 2. Okay, now there is another thing you can say that if you look at pole of order 2 of R and you write them like this, you know, plus some other point. Okay, this is a special shape we like for this kind of equation. And if you look at point x0, whose number here that appear alpha is not rational, or is 0, is not a non-zero rational, then this set of points in your curve or in your line will be invariant by your f. And the reason is that around these poles, the monodromy has infinite order because of this condition. And when you compose something that have infinite order with an algebraic map, you get also monodromy of infinite order. So when you compose your solution H with F, you get another solution, but at the point with infinite order monodromy cannot move. Or they can be permutate, but they cannot be sent in another point. So this set is invariant. This is a set I have to take out, you know, when I said my quotient is X star inside of X as a risky open. This point are problem. And then the last thing that if you have a Zariski open subset of y, if you start with R rational, then R is just a projective line. Oh, this is just a projective line, and this is a Zariski open subset. Okay. If there is a Zariski open F invariant with F a rational, an algebraic map, meaning a graph in the product of two of them, okay, an algebraic curve here, subset on which F does not ramify, mean both projection of F on CP1 have ramification in the locus we are taking out. So above this Zariski open, both projections do not ramify. Then you will find a group gamma here, okay, that realize, oh, or maybe I need an hypothesis. I need there are more than 3 points. Yes, so y hat is hyperbolic. Then you can always find H, a subgroup gamma such that this is a quotient of the upper half plane, but then you will get this for free from Schwarz lemma. Schwarz lemma, you know, that gives you the automorphism of the disk. Okay, then if you mix all this together, you have plenty of cases where you can conclude, because if the R you get has only pole of order bigger than 2, then it is not in the, okay, you can exclude that. Then if all the ramification here, alpha, are irrational, then they are invariant, and then you find your PG that is defining F. And now you have plenty of case you can do, and you can also pull back everything. Maybe, I don't know why I have X and Y in this sense, but I want to pull back. So I want X here and Y here. So you can do the construction here that we did and then pull back everything on X. That's why you have some H here. Okay. I will keep that. And what is better is to put a Y here. A Y here and a small X. Not a Y, a X, excuse me. Oh. And then you have this map. And when you pull back H of Y, when you pull back this relation, you will get a new relation between inside the Cartesian product of two Y's, and the same job will apply. So the only thing that now we have a problem when alpha is in Q. So in fact, this is a remaining case to prove what I want to prove in the previous slide. What happens if all your poles here, so you have an equation like this one with all poles having order 2 having this shape with alpha in Q. And then you want to say something about the algebraic map that map these two. So not exactly another solution, but almost another solution. I mean, you have to put some multiplicative factor here. I don't want to do, but you look at algebraic function such that each time you pick up a solution here, you compose with F, you have another solution. And this case can appear. In fact, it appears. No, it is exactly what appears in the J function. And it is what we want here. Here it appears also if you're able to kill all this by such a covering. Yeah. Here, what happened that the gamma you build is torsion free. Okay. If all the poles are irrational, then the gamma you build is torsion free. And if some poles are rational, you want to do the same with some torsion in gamma that gives you the this rational number here. And this, I don't know how to do. Really, I don't know.
So Guy,
yeah.
On this slide, your argument here is R assumed to be a rational function here, or you can do it for algebraic.
I can do rational on curve.
Right.
Yeah.
Rational
so
okay,
it's on curve, so it's algebraic.
Okay, awesome.
Yeah. So if I exclude this case, okay, I can prove the conjecture. But if you look at, I will go back to, okay, the true theorem we want to prove is Rit. Oh, yes. So this. So then we want here, we want to continue then and get a list. Yeah. So from the work of Lucia and Gladys, I think we will, they or we, I don't know, someone will be able to do the case where the subgroup is strictly, Galois group is strictly included in PSL2 of C. And in the case where it is PSL2 of C, we want a list that say, okay, the only thing that happened from arithmetics of subgroup of PSL2. If you look carefully at what I did, the gamma I build must be arithmetic subgroup. Or maybe it is not, I'm not able to prove that, but it must be, because every element must have infinite in the commutator. You must have many people. All the powers of Q must appear somewhere in the commutator.
All right, so it has to be arithmetic.
Yeah. So we want a list. So, but there exists R, but you have no information on R. You don't know from the way I prove that, I have strictly no information on R. I cannot say anything about order of poles, ramification, all this, I don't know. So each time you impose, and even if I impose something on F, I'm not able to, okay, I'm not able to translate on F the hypothesis I need on R. Otherwise, I will have a weak extension saying that, okay, if I take a solution of this equation that is differential algebraic plus some additional condition, then I have a list. But I don't know how to do that, because the condition I need on R are not easily translated in condition on F. Yeah. And so that even if I had condition on R, it's not a nice theorem. No. So if I pick up a solution, blah, 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 which is differential algebraic, and moreover, the Kummer equation that it satisfies, it became a theorem that, okay, it's not beautiful. So.
Okay. So do you have any other questions for Guy?
Okay, yeah, I have some other question, but I guess it's kind of more general or speculative compared to other ones. So if you think about the original theorem of Rit, you know, on this I guess you called it a hypertranscendence type result, where if a certain function was differential algebraic, then it had to be very special, like a Chebyshev polynomial, or
yeah, the function itself will be exponential, or cosine, or Weierstrass-P function, or variation here like p prime, and in special case, you know, a special complex multiplication case, you have p square or something like this. Yeah.
But I mean, this original theorem of Rit, having to do with like lattice maps and the rest of it, I mean, so hasn't in some ways that theorem of Rit been generalized now by like various people, like
yeah, there are generalization by I remember just one name, Berg-Weiler, and co-authors, but there are more like replace R by, for instance, an entire function, a function which is holomorphic on the whole plane, and not rational but holomorphic on the whole plane.
Yeah, but Guy, I guess I'm talking about like the theorem of Rit at the very beginning of your talk.
Permutable functions.
Yeah.
Or I can go at the very beginning. Not this beginning and this one.
Right. Yeah. So.
Or this one.
Yeah. I mean this Rit hypertranscendence theorem.
Okay.
Yeah.
So this has been generalized by letting F.
Yeah.
I put R. Excuse me. It was F. F be a little bit more general than rational function. Not general because it does not contain, but F to be entire function.
Mm-hmm. But
I don't. Yeah.
Aren't there also setups which get a similar conclusion? Like, for instance, this seems related to like the paper of Alice Medvedev and Tom Scanlon.
There are many places where these three cases appear naturally. Each time, for instance, when you're doing a complex dynamic,
right,
complex dynamic, each time you have an inequality, or not each time, 99%. When you look at the case where you have equality, this case appear. Yeah, for things about equilibrium measure, blah blah blah. There is a case where you have inequality, but if you have equality, you are in this situation here. So there are many places where they appear, and they seem more or less all related one to the other. But I mean, there is two categories. There is this Rit theorem where the same Rit list appear, and this one. And many theorems are in this situation here. Many others are in this one, but the intersection theorem that can gives you a relation between these two, I don't know. The list is the same, but go directly from this commutativity relation to this, let's say, hyper-transcendency result. I don't know.
I see. So, but I mean, for instance, isn't like the paper of Medvedev and Scanlon is like this, but rather than considering like a Q difference equation, some more general automorphism sigma is considered.
Maybe I didn't look at it.
I see. Okay, all right, thanks. Yeah.
So this guy I was talking about, Berg-Weiler and his co-author, they also look at equation really different equation, or in fact, they do not read like this because it is not so easy to understand. Z done Z plus 1, it is easier to understand Z over Z minus 1 equal to f of Z, and maybe 1 minus Z is better. It is the same, okay? And again, if you have some hypothesis on f like this one, you can ensure there is some holomorphic function f that solves this equation. But then in any case, they will be differentially transcendental or hyper-transcendental, any solution. And the proof, in fact, is really, it fits in this context. So you first, so they don't say that, but you first realize that, and then you have the solution that are in read list, and then you realize that the condition you had, which are not this one, are not satisfied by the read list. So no one.
Mm-hmm.
For very, very general automorphism here, I didn't read the paper of Scanlon and Alice. And
yeah, but I mean, in those papers and other people's sort of related results, I mean, they ended up pursuing this kind of result in part because you could say it in two ways. They wanted to understand the curves in, say, like 2 or higher space, which were invariant when each coordinate satisfies a kind of Q difference equation, like the one in red there. Yeah. And then somehow, well, maybe rather than like this kind of algebricity result or transcendence result, where they conclude something about the solutions itself, they conclude basically something about the possible algebraic relations between.
So something like the polynomial relation between f1,
yeah,
f2, fn.
Yeah.
And they are all solutions of the same Q difference, or different Q difference?
I can't quite remember the precise setup, but yeah, I think they allow for different functions, big F on each coordinate in some way. Yeah. And then those kinds of results, I guess, they have a big application in algebraic dynamics for reasons I can't explain.
And this F is rational polynomial, or it can be algebraic?
I think that they're okay. I mean,
I will see the paper.
Yeah. I don't know the exact setting, but I think the setting where the strongest applications are pursued are where F is a polynomial.
Yeah.
Yeah.
Okay, so do we have other questions for Guy? Okay, so if we don't have any questions, let us thank Guy for his nice talk.
Thank you.